Hello friends, welcome to the second lecture on transducer. So the second chapter is indicators and display devices. In this part 1 video we shall discuss with respect to indicators. In the case of indicators we need to talk about PMMC, we need to talk about MI, and we need to talk about EMMC. We need to know the construction part. Also we have to compare and contrast with respect to several parameters. So all those things we are going to discuss in this video. In the previous video we have talked about the static characteristics of an instrument. We should have the accuracy, resolution, precision, expected value, error and sensitivity. These things we have discussed. In the case of accuracy, accuracy is defined as how close your measured value with respect to a true value. In the case of resolution, the smallest change in the input for which your instrument is going to respond. Precision is nothing but a repeatability, right? Next, expected value, as I told, it is the most probable value, nothing but the practical value should be equals to the theoretical value. And error, how we are going to define? See, it is the deviation of the true value from the desired value or the measured value. Error can be positive, negative, or it can be even zero also. How we are going to define the error? In instrumentation you are going to define in one way, in digital electronics you are going to define in the other way, in signals and systems you are going to define in the other way. In some textbooks error is defined as true value minus measured value. In some cases error is defined as measured value minus true value. And in the case of sensitivity, the ratio of change in output of the instrument to the changes in the input. That's how sensitivity is defined. So these things we have discussed in the previous video. Now errors, how we are going to classify the errors? Errors you can classify into gross error, systematic error and random or residual error. In the previous video I have discussed about all these things. Now the systematic error is further classified into instrumental error, environmental error as well as observational error. In the case of instrumental error, so any error with respect to the instrument that you are going to classify into or put up into an instrumental error. Manufacturing defect, aging, loading effect, misuse of instrument, right? Aging is nothing but prolonged usage. Manufacturing defect means at the time of manufacturing only the defect do occurs. Loading effect, one example what I have given is, see, in the case of ammeter measurement, the measured value will be less than the true value. Why? In the case of ammeter design, the ammeter is going to consume some of the energy or some of the power. In order to reduce it, we are going to make use of clamp on ammeter. Misuse of instrument, as I discussed, in case of voltmeter if you are making use of an ammeter, or in the case of ammeter if you are going to make use of an voltmeter, error do occurs. Environmental error, stray magnetic field error, stray electric field error, temperature error, very important. When temperature increases, at the time you will be having a case positive temperature coefficient or negative temperature coefficient. You have to compensate it with the help of resistance, right? Maybe you can make use of a swamping resistance or any other technique you can adopt. Next, in a vague way, error can be classified into static error, which is not a function of time, and the second one is dynamic error, it is a function of time. The sources of error is very important, we have discussed. Now we have defined what do you mean by an error, what are the classification of an error, how to suppress an error, and what are the sources of an error. Next, what are the dynamic characteristics of an error? 4 things are there, that is very important. The first one is the speed of response, in turn related to lag. How fast you are getting the changes with respect to an input. Say suppose in the case of an op amp you will be having a sleeve rate. If your input is a square wave, you will be getting a ramp kind of thing, sleeve rate. How much you can reduce this? Say suppose my system response is something like this. This is the best one, this is not at all preferred. So sleeve rate is nothing but how fast your output can track the changes with respect to an input. Volts per microseconds you are going to define, right? So in turn related to lag. Fidelity, it is the degree to which an instrument indicates the changes in the measured value without any dynamic error. Faithful reproduction. Dynamic error, It is the difference between the true value of the quantity that is changing with the time and the value indicated by the instrument, provided there should be no any static error. Provided there should be no any static error. Till here we have discussed in the previous video. Now analog instruments are classified into how we are going to define or how we are going to classify. First one is a indicating type, a recording type, and integrating type. Indicating type means what? You will be having a pointer which will be having a needle deflection. This is in the case of analog. In the case of digital, you are going to come up with a value. In the case of PMMC, you are going to measure voltage or you are going to measure the current. In the case of MI, again you are going to measure voltage or current. In the case of EMMC, you can able to measure voltage, current, power. All those things are there, right? Power factor also you can able to measure. These things we shall discuss in the next slides. In the case of recording type, you will be having a pen kind of thing which will be fixed. Then upon changes with the input, it will be plotted. Seismograph, ECG and EEG. The graph, if you are seeing, you will be getting a fair idea, right? There you will not be denoting it as 2.3, 2.32, 2.35, nothing. Main thing is graph is important for you. In the case of integrating type means what? For the previous value, current value is added and so on. Say suppose your power bill reading is 5000. After 30 days, if it is 5020, nothing but what? For 20 units of power, you have to pay the power bill. For 20 units of reading, you have to pay the power bill. In the subsequent month, next month, say suppose if its reading is 5050, nothing but you have to pay the bill for 30 units which you have consumed. So it is integrating the values, or it is going to add up the values. So integrating type is used in energy meter. Very important. There are three main torques. One is a deflecting torque, a control torque, and damping torque. One simple example I am going to give you. See, say suppose this pointer is reading to 0. Maximum value is 5. Voltage, current, not at all important for us. Say suppose this pointer wants to read 4. Say suppose this pointer wants to read 4. Now from 0 to 4 it has to move. From 0 to 4 it has to move. So for this movement, what is helping means a deflecting torque is helping. At 4 it has to stop. At 4 it has to stop. Then at 4 maximum and equal opposition should be imposed by control torque. Now see, there is a force from TD and there is a force from TC also. It will make an oscillation and it stops. So whether it is going to employ underdamped system, overdamped system, critical damped system, what is the nature? It is going to taken care by damping torque. So control system topics, you are going, if you are familiar, you will be in a position to understand these things, right? So damping is used here also. In the case of networks also, you are going to speak with respect to the damping oscillations, right? Next, in the case of control torque, if I am speaking, you will be having two variants. The first one is spring control mechanism and the second one is gravity control mechanism. Gravity control mechanism means it works based on gravity. Spring control mechanism means it works based on the stiffness of the spring. Compression and expansion, that's it. The scale that is going to use in the case of spring control mechanism is a linear scale. In the case of gravity control mechanism, it is a non-linear scale. How you are going to place, what is the orientation? In the case of spring control mechanism, however you want to place, no matter. But in the case of gravity control mechanism, based on the gravity only you have to place. Maintenance or a drawback, see, spring control mechanism, stiffness you are going to reduce, right? And aging effects also will be there, temperature effects will be there. But in the case of gravity control mechanism, there is nothing like that. So this PMMC make use of spring control mechanism. At that time the scale will be a linear scale. In the case of gravity control mechanism and in the case of MI, the scale will be a non-linear scale. then the scale will be a non-linear scale. Very, very important. Now, till now I have not talked about what you mean by PMMC, MI, EMMC. Remember these things later on. Once again we can revise. In the case of air friction damping, fluid friction damping, eddy current damping, in order to push it, what is the thing you are going to use? Are you going to make use of air or fluid or eddy current? Which one is better? There we need to compare and contrast. Construction, it is simple, complex and complex. Maintenance, air, less only. In the case of fluid friction damping, you have to change it often, and there may be chance of leakage. All those things you are going to consider. Mounted horizontally or vertically. Fluid, no, one side only you can mount. The other side you want to make means a proper sealing should be there. Next, frictional part in the case of air friction damping is air. In the case of fluid friction damping, it is a fluid or which is viscous in nature. Eddy current damping, it is a current where you're going to apply the reverse current. Order of effectiveness, eddy current damping is a very much popular or the best one when compared to air friction damping. Eddy current damping is very much better when compared to air friction damping. Very, very important. Now, let us talk about a PMMC, permanent magnet moving coil, or it is also referred as a d'Orson-Wald type galvanometer. See, the construction part is very, very important. You please have an idea of it. Now, look at the things. You will be having an aluminium former. Now, consider this diagram. See, in the case of PMMC, this one we are going to call it as aluminium former. And here the current which will be carried by a spring. This N and S, what I have written, it is a permanent magnet. It is a permanent magnet. This is shaft. This is jewel bearing. Now, they are going to ask with respect to the construction part. Questions may be asked with respect to the construction part, or they can compare with respect to MI or EMMC. Now, what I have told, this PMMC is the one which will be reading the average value, nothing but the DC value it is going to measure. AC it is not going to measure. The current that will be passed through the spring will be making a movement, and then the value of the current will be calculated. Here this permanent magnet which is an horseshoe magnet made up of all nickel, aluminum, nickel and cobalt, where the magnetic field is very, very high, of the order of 0.1 to 1 Weber per meter square. Now, this is a shaft, and this is spring. This aluminium former, the advantages of aluminium former means you will be having a fixed coil and you will be having a moving coil. For the moving coil, it is going to provide a support, and it is going to offer eddy current damping. Very, very important. And see, this PMMC is going to adopt a spring control mechanism. When it is going to adopt spring control mechanism, as we discussed, the scale will be a linear scale. Right? Now, the jewel bearings are used to reduce the friction, and the the material that is used in order to fabricate it is aluminium. Now, the value that it can able to measure, it is a low value which is of the order of 20 milliamperes, and voltage is 100 millivolt. Such a low value it is reading. And on passing the high current, a spring is the one which is going to get damaged. Thereby, frictional error is going to increase and sensitivity is going to decrease, and chances is there that there may be a permanent damage in the spring. Now, this this torque is defined as force into perpendicular distance. Now, this PMMC, as I told, it is going to employ spring control mechanism. So, at a steady state, you are going to get the control torque which is equals to the damping torque. The control torque which is equals to the damping torque. The control torque is Kc times of theta, which is BNAI. So what I can tell, theta is proportional to I. Proportional means what? Can I tell it is a linear? So it employs a linear scale. It employs a linear scale. Now in this AC quantities you can't able to measure. Why? The pointer is continuously deflecting. The spring is continuously moving. So you're not in a position to measure the AC quantities. Nothing but voltage and current. So this is about PMMC. Next, in order to overcome it, we are going for MI. And then we have to talk about the difference between PMMC, MI and EMMC also. Now, with the help of PMMC, you can able to measure, or you can design for ammeter, and you can design even for voltmeter also. To increase the range of voltmeter and ammeter, the swamping resistors which is made up of manganese is used. Voltmeter design connect in series with the meter. For ammeter design connect in parallel with the meter. That's it. But for each and everything there is a drawback. Want one, you are going to lose the other. Nothing but what I want to tell you is a range increases means what? Sensitivity is going to decrease. Now let us talk about moving iron. In the case of moving iron, again you will be having the attraction type and you will be having the repulsion type. Now the accuracy of instrument which is limited to the magnetizing curve. What do you mean by all these things? Let us discuss later. One thing you have to remember that moving iron coil is suitable for high frequency measurement. In the case of moving iron, for high frequency measurements RMS value is measured, but for low frequency measurements like pointer will be oscillating continuously, thereby the value can't be read. The value can't be read. Very, very important. Now in the case of MI, see what I told, this MI can able to measure the very much high values up to 50 amperes and voltage up to 250 volts. Very, very important. Now in the case of MI ammeter design, if I am speaking, you will be having the system which is something like this. So the meter resistance I am going to define it as RM, and the meter inductance I am going to define it as LM. Very, very important. Now assume that the current is flowing, how much 0 to I1 is the current that it can able to read. Now we have to increase this value. Assume that there is no frequency variation. Frequency is constant. Then this meter is valid. Now if you want to increase the range of it, what I told, one extra resistance that we need to connect in parallel. Now one extra resistance we need to connect in parallel. So it is connected in shunt, so I am going to represent by RSH. Now the meter resistance is RM. Now it will be RM dash, LM dash, and the current. Now look at the things. Here the current that is getting into the meter, I am going to call it as I2. Why? Initially the resistance was just RM. Now one more resistance you are connected in a shunt, such that the effective resistance is decreased. Nothing but current is getting increased. So I2 is greater than I1. I2 will be greater than I1. Very, very important. So a range you have increased. Here also you have assumed the frequency is a constant. Assume that, say suppose you are increasing the frequency. Assume that in the first case you have increased the frequency. When you try to increase the frequency, Lm is a function of a frequency, nothing but omega Lm increases. When omega Lm increases, the meter impedance also increases. The meter impedance also increases. The current in the meter will decrease. The current in the meter will decrease. So, what is the measured value? The measured value will be less than the true value. The measured value will be less than the true value. So, error you got negative. Very, very important. Now, say suppose if you are decreasing the frequency. Say suppose you have decreased the frequency. Omega Lm, this quantity reduces. Zm reduces. What happens? Im increases. Theta also increases. Measured value will be greater than the true value. What is the error you got? Error is a positive. Error is positive. So, frequency error occurs. Frequency error occurs. Nothing but when there is a change in frequency, the instrument it is going to offer the error, and that need to be reduced. So, this meter is a frequency sensitive. This meter is a frequency sensitive. Very, very important. Very, very important. Now, we have to design the meter in such a way that it should be frequency insensitive. Frequency insensitive. Nothing but one quantity, if it is ranging means increasing means another on the other side it should decrease. You should make it less such that it is compensated. Now look at the thing. You have connected extra resistance. Over here. Connect one more impedance network. Your problem is solved. Why? The time constant of the meter is equals to the time constant of the parallel network what you have connected. Such that the frequency variations are reduced. Very, very important. So, this is how you are going to compensate. For meter frequency variation. See, initially meter was there which was reading the current. How much it was reading? 0 to I1. Now, what is the current it is reading? It is 0 to I2. I2 is greater than I1. Also, if there is a change in frequency, no matter why, you have incorporated this LSH. You have incorporated this inductance part such that frequency variations have been suppressed. Very, very important. Right? So, this is how you are going to compensate with respect to the ammeter ranging things. Now, let us talk about a moving iron voltmeter. Initially, you will be having meter resistance Rm. You will be having the meter impedance Lm. You will be having the voltmeter. This is the measuring part. See, what I mean to say is, this voltmeter will be having some impedance and some resistance. That part I have shown it as Rm and Lm. That's it. Now, extra resistance you are going to connect. In series. Call it as RSC. Now, this is the voltage what you are going to measure. Initially what you are going to measure. Call it as V1. No problem. Now, say suppose in this what you have done is initial part is Rm, Lm. That's it. So, actually this is the voltage reading V1. Now, you have increased the range. You have connected the resistance as in series, not only sampling resistance, any resistance of your choice you connect, nothing but a normal resistance you connect. Voltmeter range will be increased. Range increases means sensitivity decreases. V2 is greater than V1. Now, this is a function of frequency. How? Say suppose if frequency increases, omega Lm do increase, then Z increases. current in the voltmeter decreases. Theta decreases. Measured value will be less than the true value. For this, error is what? Error is negative. Error is what? Error is negative. Similarly, say suppose a frequency you are decreasing. Omega Lm decreases. Voltmeter resistance decreases. Current increases. Theta increases. Am, nothing but measured value will be greater than the true value. Error is what? Positive. Error is what? Positive. So, frequency, it is a function of frequency. So, the circuit is a function of frequency. In order to reduce it, what you are going to do? Say suppose you have connected something like this. You try to connect something like this. This is RSE. This is CE. CSE you take. No problem. This is LM. This is RM. Now, whatever the changes in the frequency occurs, you are compensated with the help of capacitance. But this compensation occurs at particular frequency only. Compensation occurs or valid at particular frequency. At particular frequency. For every frequency variations you want, means you have to change the capacitor. Variable capacitors you have to use. Or the better method is connect a circuit which is something like this. Connect a circuit which is something like this. That's it. So this is CSC. Okay. This is LM and this is RM. This is how we are going to compensate for a frequency. This is a frequency insensitive. This is a frequency insensitive. Very, very important. In the case of this moving iron ammeter, you have connected an inductance, but here you can't make use of capacitance alone. That capacitance movement part is required. Right? Very, very important. Now, what is the value of this capacitance? Lm by R square. This is based on theoretical value. But practical value is how much? 0.41 Lm divided by R square. So this is very, very important. So this is the value of the capacitance. This is the value of the capacitance. Now look at the things. In the case of Mi also you will be having the errors. In the case of Mi also you will be having the errors. So what are the errors that you are going to face in the case of moving iron? So first one is a talk about frictional errors. Frictional error. See, in this you will not be having any movement part. Spring is not going to make any movement. But in the case of in the case of PMMC, there was a movement in the spring. So frictional error is less. Frictional error is less. Second one is talk about stray magnetic field error. Now, in the case of PMMC, inside a strong magnetic was there. Outside, whatever may be the things, it was not dominating. But here, outside electric field may influence. Outside magnetic field may influence. May influence. Very, very important. Next, frequency error, you are compensated. Frequency errors need to be compensated. Need to be compensated. Already how to compensate we have discussed. How to compensate we have discussed. Next, you will be having the hysteresis error. You will be having this hysteresis error. Now look at the things. Like this you will be having. In order to reduce it, what we are going to use? This pointer. This pointer. It is going to take a linear path. For this, this pointer should be made use of NiFe, nickel iron. Nickel iron. Very, very important. Right? And then you will be having eddy current error. You will be having eddy current error. Very, very important. So in the case of MI, you will be having 5 errors. The first one is a frictional error. Frictional error is less. Stray magnetic field error, it is more. It is more. And frequency error, we have discussed how to compensate it. Hysteresis error, how to reduce it is make use of NIFE, the pointer you have to make use. And eddy current error need to be reduced. Important. This EMMC is a combination of PMMC and MI. Look at the things. MI can able to measure both AC quantities as well as DC quantities. But PMMC was in a position to measure only the DC quantities. Here also, in the case of MI, frequency should be more. Here also, in the case of MI, frequency should be more. At that time, RMS reading it is going to read. If the frequency is low, means what is the problem? The pointer will continuously oscillate. The construction part of EMMC, look at the things. Here you will be having the fixed coil 1 and you will be having the fixed coil 2. So this is the moving coil. Now in this, this is moving coil. Okay. So this is a spring. This is a jewel bearing. And this is the shaft. So all those things we have already discussed in PMMC. Now what is the function of the fixed coil, moving coil, each and everything is important. When I will be discussing with respect to the ammeter design and in the case of voltmeter design, I am going to emphasize more on it. As of now, please remember EMMC is a combination of PMMC and MI. Now look at the things. What are the errors that you are going to face in the case of EMMC? So you will be having the frictional error. Same story we are going to repeat. Frictional error which will be less, but when compared to MI it will be more. Next, stray magnetic field error which will be more. Now frequency error, you can compensate it. Frequency error is less. Now again one more error is there, hysteresis error also you are going to reduce it. Why? The eddy current you are going to reduce. Eddy currents you are going to reduce. So eddy current error you are going to reduce. Pointer, make use of one which will be a linear behavior. Now this EMMC you can able to use it as an voltmeter and you can use it as an ammeter also. In the case of ammeter design, EMMC as an ammeter. Now look at the things. You will be having the fixed coil 1 and you will be having the fixed coil 2. FC1 and FC2. You will be having the moving coil. This is a moving coil. Provide a single phase supply. Now what is the damping torque equation you will be having? IL square into dm divided by d theta. Here make use of spring control mechanism, no problem. Eddy current EMMC plus spring control mechanism. So this theta is proportional to IL square. What is the proportionality? Square, nothing but what? Non-linear scale. Very, very important. Non-linear scale. Now similarly, if you want to design an voltmeter, what is the scale you will be having? For that we are telling all these things. So you will be having the fixed coil 1, you will be having the fixed coil 2, and then you will be having the moving coil. you will be having the moving coil. So this is fixed coil 1, fixed coil 2, and then this one will be a moving coil. See, the voltage across this is a VL. Now this is Z. Now what is the equation you're going to get? Kc times of theta, which will be equals to VL square divided by Z square into dm divided by d theta. Now theta is directly proportional to VL square. Nothing but what is the nature of scale you will be having. The nature of scale will be a non-linear scale. The nature of scale will be a non-linear scale. Very, very important. Only in the case of PMMC you will be having a linear scale, but in rest of the two cases you will be having a non-linear scale. That's what we have discussed over here. Now, initially before starting with this spring control, before starting with PMMC and MI, we have discussed with respect to these things. What is the nature of scale? Whether it is linear or whether it is a non-linear. We have tried to emphasize on it. Here I have made a comparison with respect to PMMC, MI and EMMC. In the case of PMMC, it can able to measure only the DC quantity, but in the case of MI, both AC measurements and DC measurements can be done. But in the case of EMMC, voltage, current, power factor, frequency measurements also can be included. The scale here is a linear scale, but in rest of the two cases, non-linear scale. Damping is eddy current damping, air friction damping, air friction damping. Talk about the magnetic field that is being produced in terms of Weber per meter square. In the case of PMMC, 0.121. In rest of the two cases, very, very low value. Torque more in the case of PMMC. Weight more in the case of PMMC. Torque to weight ratio more in the case of PMMC. Sensitivity more in the case of PMMC. Outside error, it is less in the case of PMMC. Why? Inside magnetic field is very, very high. Frictional error is more. Why? Spring is going to make a movement. Spring is going to make a movement. You talk about EMMC, whether this frictional error is very less or less. Just comment the answer in the comment section. Current or voltage measurements can be done. What is the range? I have tried to emphasize on it. Look at the things. In the case of PMMC, moving coil will be there. But in the case of MI, you will be having a fixed coil. But in the case of EMMC, you will be having both fixed coil as well as moving coil. Very, very important. Measurement of single phase transformer without wattmeter. So in the case of 2 wattmeter method, you are going to use only 2 wattmeters. But here, without wattmeter, you are going to measure the power by using voltmeter or by using only ammeters. Right? Please go through it. Wattmeter is the one which will be reading the average value. The design part I have given over here. Blond's theorem is valid for both balanced load and unbalanced load. A star to delta network, delta to star network, what is the power equation? I have made a comparison. Please go through it. Now, this is the 2 wattmeter diagram, and here you are going to provide balanced 3-phase supply. You will be having 1 wattmeter. You'll be having 1 wattmeter, and here you will be having the another wattmeter. This is a wattmeter 1 and this is wattmeter 2. This is wattmeter 1 and this is wattmeter 2. Now look at the things. What I want to say is, if you want to measure the 3-phase power, 2 wattmeters are enough. 2 wattmeters are enough. Right? So this is the circuit diagram. But what is very much necessary is this table you have to remember. You please go through the previous year question papers. Based on this table, n number of questions they have asked. Now this power factor you are going to define in terms of cos phi. Based on the comments, this last table is important. Say suppose when phi equals to 0, you will be getting a unity power factor. Readings of 2 wattmeters are equal. Magnitude wise it will be equal. See, cos of 30 here, cos of 30, phi is 0. So you will be having root 3 times of VLIL. Here also you will be having root 3 times of VLIL. But say suppose when phi equals to 30, you will be having VLIL by 2. Here you will be having VLIL. Nothing but one wattmeter is going to read double value of the other wattmeter. Now say suppose when phi equals to 60, one of the wattmeter is going to read 0. Why? Cos of 30 plus 60 will be cos 90. Cos 90 is 0. So one of the wattmeter is going to read 0. Next, similarly, say suppose when phi equals to 30. When phi equals to 30, what you are going to get? Cos of 30 plus 90, which will be cos 120. Nothing but what? Minus sin 30. So what is the thing you are going to get? The wattmeters is going to read the equal value, but magnitude wise it will be the same. Magnitude wise it will be the same. So here also it is VLIL by 2, there in the other also it is VLIL by 2. Negative things you can't able to refer in the case of wattmeter, but for simplicity point of view you can understand that say suppose in one case it is dissipating, in the other case it will be absorbing. So magnitude wise it will be, if you are considering, means it will be the same. So friends, let us do a quick revision till now what and all the things we have discussed. Analog instruments are classified into indicating type, recording type and integrating type. In the case of indicating type, you will be having PMMC, EMI and EMMC. And you will be having three main torque. One is the deflecting torque, control torque and damping torque. What is the significance of it? They are going to ask. Say suppose if control torque is not there, the pointer will be reading the maximum value. Say suppose if the deflecting torque is not there, the pointer will never deflect. Say suppose if damping torque is absent, then the circuit or the instrument may get into continuous oscillations, or oscillations may not occur, or it may not stop, or the pointer may get damaged. In the case of control torque, you will be having spring control mechanism and you will be having gravity control mechanism. And which one will be in which one you will be having a linear scale and in which one you will be having a non-linear scale, they are going to ask. Order of effectiveness, you refer to the previous year question papers, n number of times they have asked this question. And in the case of PMMC instrument, nothing but permanent magnet moving coil, also referred as a d'Arsonval type galvanometer. Here the magnetic field is very high. Why? You are going to have a horseshoe magnet which will be made up of alnico, aluminum, nickel and cobalt, and the spring is made up of phosphor bronze, and here the spring is the one which will be carrying the current. Say suppose if you are passing the strong or the high current, the chances is there that the spring may get damaged. Here you will be having the frictional error, which is more, sensitivity do decreases. The pointer is made up of aluminum in order to reduce the eddy current dampings, and jewel bearings are used to reduce the friction. And torque, the damping torque is defined as a TD, which is proportional to, or which is equals to BNAI proportional to I. Nothing but the scale you are going to use is a linear scale. And in the case of swamping resistors, nothing but in order to increase the range, you are going to make use of swamping resistors made up of manganese. Moving iron coil, you will be having the attraction type and you will be having the repulsion type. Now look at the things. In the case of moving iron, you can design, or you can able to measure the current, you can able to measure the voltage. Initially the meter was there. To this you connect extra resistance, that is a swamping resistance in parallel. So the effective resistance get decreases, current increases. So I2 is greater than I1. In order to overcome the frequency errors or frequency fluctuations, the second circuit that is used. So this is a frequency insensitive circuits, right? So similarly we have designed even for moving iron voltmeter also. In the case of moving iron voltmeter, this increasing the range. In order to increase the range, we are going to make use of RSC. In order to compensate it, with the help of capacitance alone is not enough. That capacitance will be having a spring moment kind of thing, nothing but a variable capacitance kind of thing you have to adopt. So this circuit is a frequency insensitive circuit. In the case of MI also, you will be having the errors: frictional error, stereomagnetic field error, frequency error, hysteresis error and eddy current error. In which one which will be more, in which one it will be less, we have discussed. EMMC is a combination of both PMMC and MI, and EMMC can able to measure voltage, current, power factor as well as frequency also. But in the case of EMMC, you will be having a fixed coil and you will be having the moving coil also. In the case of moving iron, what and all the errors are there? Same things you are going to discuss in the case of EMMC also. EMMC as an ammeter, EMMC as an voltmeter we have discussed. Here the scale is a non-linear scale. Now we have made a brief comparison with respect to PMMC, MI and EMMC. Also, in which one you will be having a fixed coil and in which one you will be having a moving coil, we have discussed. And 2 wattmeter method is very important. Just try to remember this table. 2 wattmeter method is very important. Please try to remember this table. You try to mug up or you try to remember whatever the thing you want, you try to follow, but this table is very important. Refer to the previous year question papers. N number of times they have asked this question. So friends, the second unit was indicators and display devices. In the next part of the video we shall discuss with respect to the display devices. There we need to talk about LED display and we have to talk about LCD display. Also we have to talk about printers also. So friends, in this video we have talked about indicators. We have made a comparison with respect to PMMC, MI and EMMC. Also we have talked about the construction part. So friends, if you followed with this lecture, please give it a big thumbs up. Also share this video with your friends and don't forget to subscribe to my channel Craving Gyan. All the best for exams. Thank you. For test series, make use of cravinggyan.com. To stay updated with us, join our Telegram group that will be given in the description.